Today we're pricing options in C++ using the binomial tree model. If you want to get into quant finance and improve your coding skills, you have to build this. But here's the thing, if you want a high accuracy, this model can become painfully slow. And that's not even the worst of all. If you're not careful enough, the binomial tree can end up eating all of your memory. However, at the end of this video, I'm going to show you my implementation and the trick that I've used to make the space complexity constant. Okay, so we have the price of the underlying today. So if we're valuing Google calls, this is the Google price today. According to this model, the price can either go up or down in a time step. It's with the probability, and the probability of going down is the complementary event of the probability of going up. So they're mutually exclusive, of course. So when the price goes up, it's calculated with this formula right here as a factor of the price of the first step. So let's call it U for up. This takes into account the volatility and the time frame. And when it goes down, it's the inverse of that factor. Let's call it V for down. If we go to the next time step, we have again two possibilities for each node. So up and down. But pay close attention to the fact that going down from the top node yields the same result as going up from the bottom node. So this is the exact same price. Up times down or down times up. Okay, quick recap. We have the price of the underlying today, a number of steps before expiry, and the possible prices through this process and at the expiry date. How can we price the option with this? Well, we know how to price an option today. We just take the strike from the underlying price for calls or the other way around for puts. So if the strike in a call is 100 and the price at the expiry is 110, the option is worth 10, right? Also, if the price today is less, the option's value is just 0. It cannot be negative. Since the price of basically anything is the price of its future payoffs discounted by the risk-free rate, we can just use these prices that we've calculated, brought to present value and weighted by the probabilities at each time step from the expiry date. So for instance, if here the option value was 10 and here the option value was 5, the probability here was 60% and here it was 40%, you would just do 10 times 0.6 times the discount factor plus 0 times 0.4 times the discount factor, and that would be the expected value for this node. You do this for every node backwards, and you have the price. I hope this was clear, but if you still have some doubts, write them in the comments and I'll try to clarify anything I can. If what you want is rigorous mathematical proof, well, you came to the wrong video, sorry. With that being said, let's look at the code. Alright, so let's go ahead and write the main function. First of all, we'll need the parameters. So that'll be the underlying price, whatever that is, the strike price, so let's say that this is at the money, also the risk-free rate, and the volatility of the underlying. We'll also need the time to expiry and the number of steps. And then we can just call the function that we'll have to write to price the option, and we'll pass all of these parameters as arguments. We can even have a last parameter that is a boolean that says if this is a call or a put option. So let's go ahead and also calculate the put in the same function. And finally, let's just print the results. Okay, so the function is going to take a spot price, a strike, a risk-free rate, volatility, the time, and also the number of steps. And as we said, this boolean that indicates if it's a call or a put option. And of course, this returns a double. So let's go ahead and type that. And now for the function itself, we first need to calculate the time step, and that'll be the time divided by the number of steps. And we'll also need the up factor, which is just e to the power of the volatility times the square root of dt. And the down factor, which is 1 divided by the up factor. Of course, we need to include CMath to be able to use these functions. And then we need to calculate the probability. This is all pretty standard, just following the formulas. And finally, the discount factor, which is e to the power of minus r times t, or dt in this case. Okay, so now we need to calculate the prices. To do so, we're just going to use a vector, and for this vector we use the following trick. Okay, so let's look at the example in the previous whiteboard. So we have a price today, we have two prices in the next time step, and 3 prices in the following one. So let's see how we calculate this right here, which is what we want to calculate right now. So this is up, this is down, this is up again. So to calculate this one right here, we need to use this factor times the price, of course. To calculate this one right here, we need 1 less u, so that's 2 minus 1, and 1 more d in the factor, yeah? And to calculate this one right here, we need 1 less u, so 2 minus 2, that's 0. And we need 1 more d, so 1 plus 1, that's 2, times s0. Okay, right, so we just need these values then, and we don't need these whole thing. Alright, so coming back to the code, this is a vector, of course, we need to include the vector of double, and let's call this asset prices, and as we've seen, this is n plus 1 size. And then we just have to iterate through it to calculate the prices at every position. So from 0 to n included. So for the example in the whiteboard before, this would yield u squared, u times d, and d squared as a factor of the underlying. And having that, we need to initialize the option values at maturity. So this is going to be another vector of the same size as the prices vector. And for every position of the asset prices vector, we're just going to value the option. So pretty straightforward. If this is a call option, we just need to calculate the price minus the strike, and this is the max between this and 0. And for a put option, it's the other way around. So this is the strike minus the price, and that's the maximum between that and 0. So now we have a vector of option prices at maturity, but we need to calculate the price at valuation date, which is today, right? Right, so finally we need to calculate the option price. How are we going to do that? Well, let's go back to the whiteboard. Right, so let's look at the whiteboard one last time. We have this array right here. So this would be position 0, 1, and 2. And we need to propagate the price backwards so that we have the price here. How should we do this? Well, what we know is the last step. So we need to propagate this backwards. And to do that, we need to loop first through the end and then through the previous one and so on until we reach this point. Okay, so this looks like we need 2 loops. One to loop through each step and another one to go through every single value. But this is going to be reduced in every single step, right? Because here at the end we have 3 values, but here we have 2 and here we just have 1. Let's take a look at how we can do this. Okay, so let's just go ahead and write the code for that real quick. We need to loop through the steps backwards, but we'll loop through the array forward inside the nested for loop. And we just need to weight every option value by its probability and discount it in every step. And finally, let's just return the option values at the beginning, which is the current price. Okay, so let's build it, hit run, and there we go, call price and put price. But let's go a step further and check how long this took. For that, we're going to use the library chrono, which is included in the STL. And let's just take the time before pricing the options. So that's the chrono system clock now. Of course, including the chrono header. And after that, let's just go ahead and calculate the end price, which should be just the same. So let's just copy that. And we need to calculate the elapsed time, which is the end time minus the start time. But we need to cast it to milliseconds. So that's end minus start. There we go. And let's just output how long the calculation took. So that's elapsed.count. And we should be good to go. So this took 0 milliseconds. Why? Well, because it was too fast. So let's try with 100 steps. Still took 0 milliseconds. Yeah, that's the problem of working with C++, that everything is really, really fast. Okay, so with 1,000 steps, it took 18 milliseconds, and with 10,000 steps, it took 1.6 seconds. 10,000 steps in just a second and a half. Well, that is fast. Well, funny enough, we didn't need to use a tree to calculate the binomial tree model. We just needed a vector. This fact makes this implementation extremely efficient. Now, I know this is a very basic model, If you want to see some more implementations of some harder models, just let me know in the comments below. But for now, I'll see you in the next video.